move here.
exactly.
Yeah, yeah, so there's not,
Yeah, that's what I noticed. So,
I mean, we do have, um, Huawei would like to do a more granular form of PFC, and we are trying to discourage that. That we don't think it's worth tweaking that more.
no, I
So,
see.
so right now for data center bridging, I think
It's
we're
actually
done.
interesting because of all the RDMA and ROCI and all of that
Yeah.
stuff. There is still, let's say, the debate is still raging whether PFC creates congestion spreading and how to deal with it and
Well,
multiple
yeah,
solutions
yeah,
in that
yeah.
area.
Yeah, well, there's no debate that it causes, there's a lot of, I mean, we're looking at, I know, Microsoft and Mellanox are looking at, running Rocky without PFC,
Right.
just accepting doing the retransmission,
That's after.
Yeah.
doing the best congestion control.
So after this boundary latency stuff, we get to the
Transmission.
reliability,
That's- That's really,
and not this time. Yes.
yeah, yeah. Yeah,
Nice to meet you.
Okay.
Thank you for your help.
yes,
So we should get started.
Okay. I think we need to start here.
yes, yes.
Hi, good afternoon, everyone. This is the TSN tutorial we have put together with Norm Finn and Pat Taylor. I'm János Farkas from Ericsson. I am the chair of the time-sensitive networking task group. Before we start, we need to highlight that what you see here is a personal, private view of the presenters, not an official view of IEEE 802 or 802.1 or anything alike. So what we have today is, after some introduction, we dive into the details of TSN tools, TSN features, like reliability, deterministic latency, resource management. And after the tutorial, after the summary and questions and answers, we have a brief demonstration of the reliability feature recently published or finished, almost published in IEEE, which is also one of the major work items in the .NET data plane on how to provide this reliability. So this proof of concept includes both. So let's get started. Actually, there is quite wide use case interest, or many areas see TSN interesting. So there are a number of potential markets that can leverage TSN. So this is not a full list, of course. One of the key ones is industrial automation. So in Industry 4.0, TSN is kind of the new networking technology that is planned to be used. And automotive or vehicular networking is very keen on having Ethernet in the car, controlled by TSN tools. And you see many others, including 5G, that can also leverage TSN. There is work going on how to provide Ethernet transport for the front-haul interface, which is part of 5G. So TSN, what is TSN? TSN is actually one of the task groups in the IEEE 802.1 working group, which is part of the 802 Landman Standards Committee that develops landman standards and mainly focuses on the data link and physical layers. 802.1, as illustrated in the figure, sits on top of the 802 scope, this green field. Do I have a laser pointer here? So 802.1 sits here, and TSN is one of the task groups there. So 802.1 is the one that is responsible for the 802 architecture and for the interworking among the among the 802 LANs, provides also security, and also responsible for the overall management and the protocol layers above the MAC and LRC layers. TSN was actually started as audio-video bridging, so you may hear the AVB abbreviation. It was started in 2005 in order to address professional audio and video market as reflected by the name, including consumer electronics and actually automotive infotainment. So it is already, AVB is used in automotive. There's an AVNU Alliance, which is an associated group to provide conformance and marketing for AVB. It got very interesting for other use cases. And the scope of the work has been extended in the task group, and the name AVB did not reflect the extended scope, so we decided to change to cover the scope. That's why it is called now TSN today, which includes industrial and automotive and many other use cases, as I mentioned before. Okay, so what is TSN? What we are after? We are after to provide guaranteed data transport with bounded low latency, low delay variation, and extremely low loss. So TSN is in fact includes 4 add-ons to generic networking, or we can call them 4 pillars. Synchronization is one of them. It's very important and provides grounds for many other tools, queuing tools. Reliability is crucial for the mission-critical applications, and we have dedicated standards tools for reliability, like the frame replication and elimination. And well, we will see details on this shortly. This is the high-level overview. And as even the name of the group suggests, we are after low latency, for which multiple shapers and queuing mechanisms have been already developed, and the work is still ongoing. And together with the resource management, which is essential in order to provide zero congestion loss, that's what we are after. So these two are to provide the zero congestion loss, and for the reliability is against the loss due to device failure. Then I would give the word to Norm to elaborate why are we doing this and what is in scope.
Thanks, Norm Finn, Huawei. You finished talking that one? You ready?
Yes, this is your one.
Oh, okay. We're targeting real-time applications. And by real-time, I mean something happens and you have to respond to it, or something horrible will happen, like 2 parts of the machine will bang into each other, or the plane crashes. So that means what we care about is worst case latency. Most of the applications, not all of them by any means, but many of the applications are control loops. I measure something, I respond to it. I measure something, I respond to it and cause an action. Control theory depends very strongly on what's the period of your control loop. And so getting the information there before you need it doesn't help anything, because I have to do the thing at the time that's scheduled to do it. So all that matters is that you get there soon enough. Average, mean, best case latencies are completely irrelevant. So that's not what we commonly think of as optimizing, because I'm not optimizing, for example, buffer occupancy. 2 fundamental ways to bound your latency: throw away anything that's late, grossly over provision the network, lots of intensive engineering or testing, or provide zero congestion loss. We chose the latter solution. So what am I talking about? I've got several hops. At each hop there are some queues. Now, if the given is constant input rate, and I should flag you here, we can't solve everybody's problems. There's one kind of problem that we are interested in solving, and that's constant bitrate streams. If you have a widely varying bitrate stream, we can't help you. It's got to be relatively constant. And it has to be last long enough that it's worth your effort to make a reservation for resources before you start using it. So assuming you've satisfied that, given that you have a constant input rate, you want a constant output rate, otherwise you're filling up or you're draining. So in the long term, the output has to equal the input. We find that then the latency is necessarily bounded if you're not throwing anything away. So how do we get zero congestion loss? What we do is at every hop, the packets per interval in equals the packets per interval out. The data rate in equals the data rate out. Now, packetized data is not a constant bit rate stream, and I typically have a bunch of streams that I want to do this with, all going out the same port. They have different data rates, so I can't perfectly space everything. So there are going to be gaps and bursts in each individual flow. So what we do in TSN is we reserve enough buffer space. We reserve the buffer space before the flow starts. We use a queuing and a queuing and shaping discipline that minimizes the interference between flows, and also provides a predictable gap and burst behavior so that we can figure out what is the worst case of the bursts versus gaps in two adjacent hops. That tells us how many packets we have to buffer in each node to ensure that we never miss an opportunity to transmit. So that when it's my flow's turn to transmit, I have to have a packet there. That means I have to have a buffer of a few packets. So we want queuing algorithms that will give us a small number of, the smallest number of packets, because that gives us the best latency. But it's got to be predictable. It's number one thing. And then for certain known delay variations, for example, it may take a varying amount of time to get from the input port to the output queue. It may take a slightly varying amount of time to get from the output queue, having selected for output, until it actually hits the wire. There are lots of variations in there. You have to have a little bit of extra buffer for the variations, because the variation in delivery time means you're storing data. That's the only way you can have a variation in delivery time, is that you're storing data. And when that time varies, you wind up dumping the data. There has to be a place for it. So, having computed the buffer space, we can get the latency. Now, to give you an idea of what we're doing, the usual best effort kinds of service. Oh, this doesn't have a, okay. The usual best effort kinds of service, the more buffers you allocate, the fewer you drop. Where is it? That one. Thank you. Okay. The more buffers you allocate, the fewer packets you drop. If you look at what is the latency for an average packet, you find there's a minimum. It's got to get to where it's going. So there's a minimum latency. Most packets don't take too long because the network is typically not congested. But if the network's a bit congested, some packets can take a longer time. Some packets can take a really long time. If there's a topology change, it gets ridiculously long. And the variation in latency, most packets occur at roughly the same time near that peak, but you can have very long latencies. So if I'm trying to engineer my network and I say, this is pretty good, but this is my cutoff. If I want this to be my cutoff, and I say I don't want anything to take any longer than that to get end to end. This is the worst end-to-end latency I can accept. If I push that in from a higher number, that means I have to drop packets. That's the way, and that's what we don't want to do. So what we do instead is we try to come up with a scheme such that we know how many buffers it takes so that I'll never lose one. If I exceed that number of buffers, doesn't matter. I've still got some residual packet loss because boxes can fail, wires can fail, cosmic rays can hit the packet. My latency is now a curve that has a minimum because it takes a certain amount of time to get there no matter what, but I've got a maximum latency that I do not exceed, and there is no tail past that. Typically, that maximum latency, there's my average latency. My average latency is typically somewhat higher than it would be if I simply gave the packets higher priority. That diagram right there is the difference between TSN and what we want to do with DetNet and typical best ever algorithms. So why TSN? Without TSN, you can do it. You can over-provision the network. You can use priorities. You can try to set the timing on your transmitters so that they don't interfere too much. There's lots of things you can do, and it winds up being, and people do this today a lot, and they wind up having to spend a very long time testing, especially the corner cases, especially what happens when I stop these 3 machines and the other 2 machines are still running. You can make it work, but with TSN, it's trivial to engineer because you ask it, will that work? Yes. Because the algorithms we use give you a yes or no answer. Can you add this stream? It works even when you have the hard to test corner cases. Shutting off all but one stream does not cause the one stream to suddenly burst or change the way it works, which makes it cheaper because your people costs go way down, and because you can use the same network for the TSN and for ordinary traffic. I mentioned the only thing that makes that tail, that keeps the curve on the tail, no matter how many buffers you have, is failures. Failures of links, failures of packets, failures of devices. So there is one other big technique that we use, which is per packet redundancy. Now, the normal way you do redundancy is you have 2 paths from A to B taking different routes through the network, and you use one path, and if you discover it fails, you switch over to the other path. Sometimes you send the packets on both paths, sometimes you don't, but you notice that it failed and you switch over. This is kind of like that, except what we do is we serial number every packet, and we receive both packets from both streams, or all 3 streams, or however many you have. And by looking at the serial number, we throw away the ones we don't want. So there is no detect failure cycle and respond to the failure with some kind of action. That doesn't happen. We're always taking both paths. And that means that it would be unusual to lose even one packet, even if something goes down, even if something goes intermittent. We've all had the experience of a link starts to degrade. You start to lose more and more packets from it. At some point, after losing a bunch of packets, you decide it's out of its service parameters. It's giving you too many errors. Now you switch over. In the whole process, you lose a lot of packets. The idea is here, you don't lose any packets so that you can get extremely low packet loss rates, even on the long term. We have another important thing, which is the packets come in, we have filtering and policing, and then the queuing, shaping, and output. This doesn't show the forwarding, but of course there's a forwarding choice in here too. An important part of this is that you can't have misbehaving streams mess up well-behaved streams. If you look at a system with lots of parts, especially a real-time system, packets flying everywhere, it's extremely, extremely hard to analyze all failure modes. Okay? And these things go into airplanes, they go into automobiles, where such analysis is very, very important because people can die if you don't. So, it's important to reduce the number of failure cases, sometimes even at the expense of perhaps increasing the chances of a failure, as long as you can analyze what will happen and show that it's okay that if it happens. So every frame we can identify which flow it belongs to. We can mark it the usual red, green, yellow. We can also have timed gates that say, this port is open for packets of this type, now it's closed. So we can insist that the brake sensor not only transmit only the brake sensor packets, but it only transmits it at these times when it's supposed to, and that it only transmit the one. Okay? Now, a brake sensor that runs off at the mouth and starts transmitting continuously can't screw up the rest of the car. Various ways to deal with that. Maybe you turn it up. We have, in our standard, we have various ways to deal with that. Maybe you drop the offending packet. Maybe you cut off the offending port. One bad thing about that is that maybe you programmed it wrong, so don't. Fix that in testing. But on the other hand, when it comes to running off at the mouth, so what is it transmitting? Well, that's a good question. That's a lot of failure modes. If it's transmitting too many packets when it shouldn't, then you know something's wrong. And I guarantee your failure analysis did include the case where that thing dies. So if it does anything weird, you shut it down. Your failure analysis has covered that. That's a good thing when you're trying to figure out what's broken. So we can protect against bandwidth violations. The decisions can be per stream, per priority. We have the gate can be operated on a time schedule. All of the devices can be synchronized so the time schedules are running all the time. So I can set my input gate to match the output gate at the other side. And now we have the next section for Janos to take.
Okay, so after the reliability aspects, which is includes protection in the ingress, let's see what happens on the other box at the output port, the queuing mechanisms, in order to provide deterministic latency. I guess you are all familiar with the strict parity queuing, where it was started in 1998. So that was the basic queuing mechanism we had, and to that, weighted queues were added with simple hooks in order to not to overspecify the details. And this is the first mechanism that was actually specified by the AVB test group for audio video bridging streams at the time. It is called credit-based shaper. I will explain in the next slide why the name. This is so the shape queues. Oops, laser pointer. The shape queues are these. So this is in these diagrams the marking for the shapes. The shape queues have higher priority than any other queues, and this mechanism still guarantees bandwidth to the highest priority that is not shaped, like priority 7 in this example. The credit-based shaper is similar to a typical run rate, burst rate shaper, but very nice with very nice properties. It has only one parameter to set up, and as I mentioned already, the impact on other queues or the number of adjacent shapers is tractable, and it doesn't depend the impact to the other queues on how many shapers you use. Let's see what it is. So why it is credit-based shaper. So in the idle period, here in the idle slope, each queue or the queues collect credit, which are used actually when a frame is transmitted. So the credit goes down when a frame gets transmitted. So if you go negative with your credits, then no transmission is possible from that queue. So that's actually a key difference compared to token bucket, that the credit can go negative. This credit accumulation can be weighted, so you can add the weighted aspects if you want to the credit-based shaper operation. So that's the AVB queuing, if you heard that term. And what I'm explaining from now on was specified as TSN. Well, it's all one package together today. So this is called scheduled traffic, which introduces time-based scheduling to the queues. It is to reduce the delay variation for CBR streams, which are periodic with known timing. Actually, it is time-based programming of the bridging queues, the 8 queues, and the tool is these time gates up front of each queue. So there is a gate before the transmission selection up front of each queue, which can be open and closed. And these gates are programmed according to the time. So it gives a time schedule, and of course, you need to know the time. So time synchronization is needed. So you can establish time slots or can do quite fancy things with this tool, the time-gated queues. For example, the time-gated queues are the basic tool we use for the cyclic queuing and forwarding, which is, in a sense, uses double buffers to establish cycles in the network. And the goal is that each packet spends exactly one cycle at each hop. This example shows 2 pairs, so 4 and 5 are 1 pair, that's green and blue, and 2 and 3 are as well 1 pair. But let's focus on a pair of queues. So what happens is that the frames that you receive are collected for a certain time period, and then with one of the queues, and then they are transmitted, and the collection happens in the other queue. So the 2 queues are served in an alternate fashion, and that's what provides the cyclic queuing. And in order to achieve this alternate operation, we use the time gates up front of the queue. So actually, we program the time gates according to the cycle time we want to achieve. What I described or actually all of us described up to this point are all done work, published or close to published standards. The next slide is ongoing work. It is called asynchronous traffic shaping, which aims to provide zero congestion loss without time synchronization. So what happens is that we aim to smoothen the traffic pattern by shaping per hop and give priority to urgent traffic over more relaxed traffic. This figure illustrates it. So what you see, these are the classic 8 queues. So this is a kind of, you can see it as a kind of hierarchical queuing that up front, before that, using the ingress filtering and policing tools we have specified and provides a lots of possibilities to play with. One of them is to implement asynchronous traffic shaping. So that's where the decision is made which flow or which packet is more urgent than the other. And then after making that decision, they get into the regular 8 queues. So that's how the shaping from one hop to another is implemented. And I give the word to Pat, who was the editor of the frame preemption standard.
Right. So I was the editor for the frame preemptions, the part of preemption that went in 802.3, because in this case, this is a facility that needs to be supported by the MAC as well as by the part of the link layer above the MAC. So when we have the scheduled traffic, that scheduled traffic is like rocks during the transmission time. That those rocks can't move; they always happen in that spot.
Now, we would like to handle the non-scheduled traffic, the traditional network traffic, as efficiently as possible, and use the bandwidth between the rocks to send as much of that traffic as we can. Now, if we just leave things as they are and send them, we'll have the situation shown here where, let's see, where's the, okay.
Just to forward. That's it. Oh,
Oh,
there's
did I
one
get the
more.
light? Ah, that's the light. Okay. So, you know, here we've sent packet 1 in this gap, and then we have packet 2 to send, but it's a little too large for the remaining gap, so this bandwidth is wasted. And then it doesn't fit in this gap either, and so the bandwidth is again wasted. And finally, here we get a gap big enough to send packet 2. That's without preemption. When we add preemption, we let the traditional traffic act like sand between the rocks. So in this case, it's okay that there's not enough room to finish sending packet 2. We can start it here and use the bandwidth, and then when the scheduled rock finishes, then we can finish sending packet 2 and start sending 3, and again, continue it after the next scheduled rock. So that's why we did it, so we could efficiently use the bandwidth while having the scheduled traffic in there and the traditional traffic sharing the same links. So we also put in something called hold and release. Now, it's not needed all the time. Preemption doesn't happen the minute you say, I want to preempt the packet that's going. For one thing, in order to be compatible with all the physical layers out there and have them not have to know that preemption was going on, we wanted the fragments that we create to look as much like regular packets to the physical layer as possible. So that included keeping the minimum size of 64 bytes. So if the packet has less than 64 bytes left to transmit, we can't preempt it. If the whole packet was less than 124 octets, then we can't preempt it, because we have to be able to divide it into 2 groups. Actually, if it has to be 128 in order to preempt it, because we have to be able to get 2 64s. And the extra CRC we add counts in that, which is why it comes out to being 124. And then in many use cases, we can stand that amount of delay. We don't need to do anything special, and we just, when we want to send an express packet, a packet that can preempt the preemptible traffic, we just send it and go ahead and live with the fact that that doesn't happen instantaneously, that we have to get to the end of the current packet or get to the point where we preempt and have an interframe gap. But for the most tight timing, for where we want to have really minimize the amount of jitter on the scheduled traffic, we have the hold and release. So we know the scheduled rock is coming up. Basically, we have a guard band of time before that happens that we send a primitive called hold to the MAC, and the MAC then will go ahead and preempt, even though we aren't giving it the scheduled packet yet. It will go ahead and preempt, and so that then when the scheduled packet arrives, we will transmit that right away. We will already have completed preemption, and there can be a number of packets that go, and then we'll release it when we get to the end of the scheduled time, and we're ready to let the other traffic flow again. So this is just a picture of kind of how this all fits in with the queues. So the queues are up here, and in order to support preemption, we basically have 2 MACs, one MAC that's handling the express traffic and one that's handling the preemptible traffic, so that this one can pause its transmission and then resume it when the express frames are done. And so the queues for the express traffic go to the transmission selection and to the MAC control for the express MAC, and the other queues go to the preemptible MAC. And then below the MACs, we have the MAC merge sublayer, which is a shim sublayer that basically takes the output of these two and does the actual preemption when necessary. And then we have below that the PHY, which is a regular PHY and doesn't have to know anything about preemption going on. I'm not going to go into the details of this. This is the structures we made for handling the fragment formats. And basically the principles here were to make the fragments look, again, as much like a regular packet as possible. So the physical layer doesn't see anything other than what it expects to see. And also to minimize the amount of bandwidth taken when you fragment a packet. To the extent possible, consistent with the first one. So basically, the encapsulation is designed so that if you're not fragmenting, there's no extra bandwidth needed. So anytime you don't preempt a packet, it takes the same amount of time on the wire as it would if there was no preemption on the link at all. And then when we do preempt, we have some extra bytes we need for protecting the data integrity, but we keep those down to a minimum. So basically, and the data integrity goal is to keep the same data integrity that we have without preemption operating. So we make sure that there's some bytes in there that keep us from reassembling fragments incorrectly to make a Franken packet, a packet that had a missing fragment or had fragments from parts of two packets, so that we keep the same level of protection as the Ethernet CRC gives us in unpreempted traffic. And Janos.
Okay, so after these, let's take a look on the fourth pillar, the resources. So what do we have on that front in TSN? We have a document describes that in QCC that describes TSN configuration and the three approaches we can have in TSN. One of them is the fully distributed model. That actually means you use distributed protocols for resource protocol for resource reservation. We have next slide explains a bit on the already existing distributed protocol, and we have recently started the development of a new one in order to provide better scalability. The fully centralized model is when both network equipment like the bridges and the end stations, hosts, are under control of a central entity, which can happen, for example, in a factory, that all the end stations and the bridges are desired to be under the control of the same entity. And the one that is also illustrated in the bottom is the centralized network distributed user model, where the bridges, the network nodes, are under the control of a central entity, which is called in this document central network configuration entity. And but the end stations, listeners, and talkers are not under the control. There is some protocol exchange or some information exchange between the end stations and the network, actually via a user network interface. This document provides information model and YANG for TSN configuration. It is still an ongoing project, yes. Yeah, I guess maybe it's good. Yeah, it's a good point. So what you see here, when you see P up front of an abbreviation, that means that's still an ongoing project. If P is not there, then the work is done. Sorry, which one is? Well, for this, this is not for data centers, but a vSwitch sits in. So there are data center bridging standards. The question was whether a vSwitch is a bridge or an end station. And in DCB standards, we have a protocol exchange and so on when it sits in. So it's treated as sitting in an end station. But this is more for TSN, so we don't have vSwitch in this figure. So these end stations here are sources and sinks of CBR streams, and what we are after is how to provide the resources for those streams in order to provide the bounded low latency. As I mentioned, we have a protocol, a standard protocol, SRP, for the reservation of resources. So this is a distributed protocol that advertises the streams, registers the paths for the streams, even calculates the worst case latency end to end, and establishes the domain for AVB domain, what is it called, that can be used by the stream, so have the same characteristics or setups in the bridge, and ultimately, of course, reserves the bandwidth for the streams. The QCC project also provides enhancements to the SRP, the stream reservation protocol. And we have a new work that has been recently started called the Link Local Registration Protocol. It is the foundation of a new reservation protocol to replicate and register the data that is needed, including the changes. And what we are after is better scalability. So we want to optimize it in the order of the database in the order of 1 megabyte. I need to highlight here that this work is not tied to bridges, so can be applied on other network nodes as well. So this is what we planned to talk about, and we have some stuff going on and available. We have no time to talk about, just to flash time synchronization. I mentioned in the beginning, it is very important. Like for example, for the time-gated queues, you have to know the time to program your schedule, or for the cyclic queuing, and we have standard for that, the 802.1 AS timing and synchronization, which is a profile of the IEEE 1588 precision time protocol for layer 2 Ethernet bridges. And there's an ongoing revision of this standard that includes addressing all these aspects, for example, providing better reliability. Security is very important, of course, in all applications, but there are upcoming use cases. I mentioned automotive networking, where it is a hot topic, how to make it secure. So this is just a set what we have in 802.1. Again, no time to talk or dive into the details. So to summarize, TSN has these 4 pillars: synchronization, for which we have the 802.1 AS specification; reliability, which covers multiple aspects, as we heard; the replication and elimination for against protection for or providing extremely low loss protection for device failures; and all the rest for protection against misbehaving streams; and the shapers queuing mechanisms to provide the latency together with the resource management in order to achieve the zero congestion loss. There is a survey for each tutorial. This is the link for this particular one. Please fill in the survey, and there's time for questions.
Hi, thanks for the information. You mentioned there was different types of scheduling algorithms you're looking at. And it sounded like at least one of them would not deliver early as well as not deliver late, right? So it was just as worried about early delivery as late delivery.
Yes.
But the other one I wasn't clear about, and you may have said it, and then maybe jet lagged and just missed it. But the one that's under development, does that also worry about early delivery?
So
I don't know if you want to flip
will,
back to it.
well, that will not deliver early either. So there is a, what is it called? There is a, so there is a timing you give for each flow when it can go out.
Yeah.
So that's what
it's-
happens in the higher, if you think of it as higher hierarchical queuing, that happens at the first step, expedited time. Yeah,
Yeah, it
that's
was actually that exact
yes,
point that
yes.
I wasn't sure about, because since it was almost, you could look at it as strict priority queuing, it meant that if something was, if you had a packet there, but you weren't quite ready to send it, does it block completely? Or
No,
would
no,
it
no,
go
no,
send a
no.
lower priority?
Yes.
And
We have two kinds of queuing mechanisms, and one kind is synchronized time-based, and the other is very much like int-serve, for those of you who are very old. And the ones that are like int-serve can deliver early if the source varies its speed, and there's a certain amount of jitter on the output. It takes it a while for all the buffers to fill up before it becomes stable, and so the jitter decreases with time, but you start all over again if you shut up and start over again, just like very much like int-serve. The other is time-based, and the time-based ones with synchronized clocks can deliver the packet within a fixed time window that's the same for all flows that are coming out of that port, or it can be down to a nanosecond if you want to do that. That gets a little tricky because of how many queues it will take and how many timers you have to handle a lot of different flows, but it can be very accurate.
yeah, I was asking it, I got on the very accurate one that you wouldn't deliver early. It was really on this one where it wasn't clear. And I think I heard Janos say it won't deliver early.
This is
and
the
I
one
think
that can deliver. This one can deliver early.
it can deliver early.
Yes.
Okay.
If the flow is running and you stop for a while and then send one packet, it'll go through real quick.
Yeah, what's a while, right? And
Because the buckets are all empty.
right.
Thank you.
I have two questions. So the first one has to do with the source and the destination, which looks like, if I got it right, they are excluded. And many times, I don't know what the assumption is for what type of devices those are, but many times significant amount of jitter and latency can occur at both ends. So how is that actually addressed here in the overall scheme?
So the one of the use cases is industrial automation, and in those cases, the sources and destinations are controllers and actuators, and the control flow is a CBR flow for the control loop between those. So that is very periodic, and that's why we can have these time-based mechanisms in the queues too.
Okay, and the other one, so obviously IEEE is 8 queues, but you may have many flows. So what is in each priority level? So what is the mechanism by which you are dealing with competing flows?
So yes, it's 8 queues, and it's up to you. I mean, you can allocate for competing, or I mean, put competing flows into different queues, and then you can have some control on those. Or what you can do is this in this green box, that the person filtering and policing that can make you can do very fancy things before they end actually in the queue, before the packets are put in the queue. And this is what the asynchronous traffic shaping uses, like internal priority value, for example,
And If I were building a strictly standard box, I'd be limited to 8 queues. If I were building something, if I were building a product for somebody, I'd very likely have a lot more than 8 queues. So
Still at the wire level, I'm going to have that interference no matter what. And so are we, so is that something that you guys are interested in the IETF to work with you on, or what is the areas that you're looking for? Because IEEE obviously is limited at some point, and the question is, exactly as you said, if I would build a product that does that, I obviously am not going to be satisfied with the number 8. So how are we dealing with that to create an end-to-end story?
Right. So realize that the per stream part, the per stream filtering and queuing, that can be operating. That's not limited to the 8 queues. That's looking at the stream characteristics to figure out what stream the flow is in. So yeah, the final gating onto the network is in the priority queues, but there's also the filtering and queuing.
And a stream is loosely defined as a 5-tuple?
Yes.
Yes,
Well,
that's one way. You can have multiple IDs.
we have a standard 802.1 CB that allows you to identify the flow. Right now, it's by MAC addresses, VLANs, and IP5 tuples. Okay, right now. And a casual reader of the standard will see that it's really easy to add.
Other identifiers.
You know, if you can do those flow, it's obvious how to do the others. And stay within the standard. Yes.
Okay.
I think that answers it.
Okay, thank you. This was very educational. Thank you.
I remember. You asked one other thing. Yes, this is packet based. It's not a bitwise CBR. Okay, so yes, there will always be stagger on the output because we're outputting packets.
Okay, and in the slide deck, you can find some references to further reading. And as I mentioned, we have a brief demo of one of the features. Yes, one more question? Yes, definitely. This is very related to .NET.
Yeah.
Okay, so maybe.
So Lou and I co-chair DetNet, and the purpose of DetNet is obviously there's a lot of networks that aren't pure layer 2 networks, and we still want to provide these kinds of capabilities over layer 3 networks as well as over layer 2 networks. And so the purpose of DetNet is to provide the capabilities to handle this kind of traffic and set up the reservations and the flows and such, so that we get these behaviors over layer 3 networks and not just over layer 2. So extending this up to the IETF domain. And we meet Thursday, yes, we're meeting Thursday morning this week.
Yeah, thank you for highlighting it. And what is coming is actually .NET as well. So as I already mentioned in the data plane, that was one of the hot topics on how to provide this frame or packet replication and elimination for the reliability in a layer 3 data plane. So what we have here is a proof of concept demo, both showing the layer 2 and the layer 3 data plane, and the packet or frame replication and elimination feature for reliability. So we focus on the reliability aspect in this case. And at layer 2, it is frame replication and elimination for reliability. So the 802.1 CB specification provides you the mechanism, actually includes a pseudocode, and provides the layer 2 data plane details. And in the .NET document called the .NET data plane solution, linked here, that provides the layer 3 data plane aspects. And in that document, it is called the packet replication and elimination function. So that's why the two abbreviations. Both are, as explained below, as it was explained during the tutorial, both of them based on having disjoint parts and sending the identical copies with a sequence number to the elimination point, which gets rid of the surplus. So what you can see here is a remote control of a balancing robot. So there is a Lego robot down there, and the control logic of the balancing logic has been moved away actually to that laptop computer. We have implemented the replication elimination function on PCs. Actually, they are in the two tower PCs. These are the pink ones here in the figure. And as a reference, comparing the replication and elimination, we compare it with 50 millisec protection switching. So as I mentioned, this is the setup that the two towers are the replication and elimination functions, and this is a ring topology, and the two pieces in the middle that are the simple switches. When we take a look on the layer 2 data plane, the controller sends VLAN tag the traffic to the edge node, and this CB mechanism adds a so-called R tag, which includes the sequence number for the replication and elimination. At layer 3, if the layer 3 network is used to provide a TSN service, so we have the same and hosts, then at the UNI we have the same format. In case of an MPLS data plane, we have the MPLS transport label, and then we need a pseudo wire label, and in case of the feature, the control word is mandatory. So we will have a .NET control word, which includes the sequence number, and all the rest become payload with respect to .NET. This is just a Wireshark capture on the wire, and so let's see the demo part. So the first scenario is when we have a link failure, and if we use a protection switching mechanism with the working tunnel, protection tunnel scheme, then we can get 50 millisec failover. There are many mechanisms for that, and the application will be impacted. When we turn on the replication and elimination, then actually the packet loss is eliminated. So let's see. So the first case is when the protection switching is on, the replication elimination is not. Yes, you can come. Yes. So what happens is you have to start the robot in a vertical position, and then the balancing learns, and so the balancing runs on the laptop. So it is a software link failure for now. At the end, we will see the physical link unplugging. It's easier for the demo for now to have a software link cut as illustrated in the figure. And this was the 50 millisec failover time. So that amount of, I guess it was 3 or 4 packets that have been lost. Typically it is. That was too much for the balancing logic. And now we do it with the replication elimination feature. So despite of the link failure, nothing survives. One of the flows, that was something else. That was the demo demon. Let's see it again. Yes, yes, you see it's real. So it survives. We have one of the flows in the redundant path. So we have actually, with the replication, it's on both flows. Actually, this is very sensitive, this guy. So if you touch it when it tries to balance, that's over. Or maybe.
I see you're very interested in the demo.
If I may add, it may be unusual to the if I may add, it may be unusual to the IETF, but it's a very classical metric for the applications in industrial control loops. The number of loss in a row is very critical. Like usual they will always let you lose a packet, but if you lose 3-4 packets in a row, they will stop the production line. If they have to stop the production line like twice in a year, your hardware is on the curb.
Yes. So let's see the other failure scenario, which we call link flapping, when link goes up, goes down. And if it is, as illustrated in the figure, 20 milliseconds, then the monitoring mechanism you use for the classic protection switching doesn't even detect. But as just Pascal explained, that can be critical for a control loop. It's very sensitive, so even not that easy to start it. Yes, that's the control. That's strange. Yeah, it's. Okay, so this is the link flapping without the replication elimination. So that's not any better than the simple failure was. So let's see it with the frame application and elimination. So multiple failures or multiple link downs, as illustrated in the figure.
By the elevator?
It's control, yeah, the control loop.
3? Yeah, well, whenever the demo's done.
Yeah.
Yeah, it should be 10 minutes, yeah.
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 Okay.
On this level, Jody?
And so this is the flapping, and of course it works with physical failure. So if we can restart again, I will unplug the link shown in the figure. So thank you very much for your attention. If you are interested in the Wireshark capture, please come to the screen. Thank you.